So we're going to talk a little bit about how to do an ANOVA test today. And I think the first thing I want to do is really talk about why or what an ANOVA test is. Let's see if this is working. Okay. So ANOVA is kind of a condensed form of a larger test called the analysis of variance. And what I'm going to do is talk a little bit about when do we use it, why do we use it, and how do we use it. And then once we do all of that, we'll talk about graphing and how to make appropriate graphs of our data. So feel free to skip through this as you need to, but it would be really important for you to know when, why, and how we use these ANOVA tests. So let's go and answer some of these. So when do we use them? So this is really to do some hypothesis testing. When there are three or more means for different populations. And a population biology is a little bit, it's a little bit different than what we're talking about in statistics. So in this case, a population's basically your group. Population. So I'm going to work a sample one after I go through these three questions. So if we have three or more populations or groups, then we're going to use an ANOVA test. Essentially, what this is an extended t-test. But an ANOVA test is the appropriate way to do that. You could do multiple t-tests, but if you think about this, even if you have only three groups for a t-test, you actually have to do two separate t-tests comparing each of the groups. But, is that right? Sorry, three t-tests. If you did 5 groups, which is your minimum for your IA, it's going to be a little bit more than that. So you have a lot of t-tests. There's no reason to do that, all those t-tests, unless it's necessary. So you start with this ANOVA test. You may need to go do a t-test later, but we'll talk more about that later. So why? What we're really trying to do is to determine if we can refute or support the null hypothesis, which in turn influences what we call our alternative hypothesis, which is really, despite even if you think there's not going to be a difference in your data, your alternate hypothesis is whatever prediction you make, whichever group is going to be better than the other. But really, what it ultimately does is indicates a difference in the DV of your experiment. And it's the difference between your levels of your independent variable. What your null hypothesis is essentially saying is that the mean of one group is going to equal the mean of another group, and so on. But this, of course, accounts for standard deviation. And that's what these tests are for. So that's what the ANOVA test allows us to determine. And how do we do it? Well, we're going to use Excel. And I apologize because everything we've done so far as stats goes has been using Google spreadsheets. But I have not figured out an easy way to do an ANOVA test in Google spreadsheets. So you're going to need Excel, and you're going to need something called a stat pack, which you may or may not have at home on your home computer, but we definitely do have it on the school computers. I'm going to walk you through how to install that stat pack to run a single factor ANOVA. I guess that's what we should talk about, is a single, we'll make this a single factor ANOVA test, which really means there's one independent variable. But you might be thinking, Mr. Tell, don't all experiments have to have one independent variable? And again, I'll tell you, we lie to you about that. There can be multiple independent variables. If there are 2 independent variables, it's called a 2-factor ANOVA. If there are 3 independent variables, we call it a 3-factor ANOVA. Okay? So, this is what we're going to do, and I'm going to now show you how we do it, how to interpret it, and then how to graph it. Okay? So I'm going to go and open up my Excel spreadsheet here. I'm going to move my screen around just, oops, that's not what I meant to click. I'm going to move my viewable screen around just a little bit here. Let's see if I can't stretch it anymore. Okay, so what I have here, let's see if I can figure out how to move this over a little bit. Okay, so what I have here is my title, which really is the volume of oxygen, milliliters plus or minus 0.5 milliliters, and I'll be honest, I just made that up. That's not very correct. In fact, it's not correct. It doesn't match the data, but I'll let you figure that out for yourself. That's not what this video is about. It's got a full title. I've got my temperature ranges, so I tested my data at 10, 20, 30, 40, 50, 60, 70 degrees Celsius. I repeated my data 10 times, and here's my data. Now, the first thing I want you to notice is that not all of my data is consistently written, and that would be a point off. So I think that that's something that you should fix, and so let's go ahead and fix that right now. So I'm going to select all my data. I'm going to right-click and go to Format Cells. And what I'm going to do is click on number, and I want 2 decimal places to match my uncertainty. I know my certainty is at least to the 10th level. That's how I know 1.7. But my uncertainty is going to be to the 100th place, plus or minus 0.05 milliliters. So what I'm going to do is make sure I have 2 decimal places, and once I do that, you'll notice that every single number here ends with a 0, and that's key. That's something to really pay attention to. But they all match formatting. What's interesting is that the significant digits don't matter for biology. It's the decimal places. So please take special note of that. Alright, so I'm going to do my standard calculations. I'm going to calculate my mean and my standard deviation and go through that pretty quickly because you've done this before. Click on f of x here and then click on average. Get my data of those cells. Boom. Now, one thing I'll tell you is that once I've calculated my mean, I've actually processed my data, and that's not written correctly. Actually, whenever you process your data, you need to go 1 more decimal place. So we'll go back to Format Cells and to Number, and I want to go to 3 decimal places now. And again, I'm ending with 0, but I go 1 more decimal place for any time I process the data, anytime I do anything with the raw data. So you measured your masses, but once you converted that to differences in mass or percent difference, all of that needs the extra decimal place. It's not that every time you process your data you add a decimal place. It's all processed data needs 1 more decimal place than your raw data. The reason being that if I were to average the number 1 and the number 2 and left in the same number of decimal places, well, 1 plus 2 is 3 divided by 2 to find my average. I get 1.5. I've automatically gone 1 decimal place beyond the original numbers of 1 and 2. If I didn't do that, I'd have to round my 1.5 to 2, which would mean that the average of 1 and 2 is 2. And I think you understand why that's confusing. So always follow that basic rule. So I'm going to do the same thing here for standard deviation. We'll click on fx or function. I'm going to go ahead and type in stdev. It's right here anyways. I'm going to click that. And again, I'm going to pick the same data points, making sure not to pick my mean. Click OK. And I'm going to go pull that equation all the way across. And now I've got my mean and my standard deviation. So what I'm going to do actually is pull this data down. And this is my raw, well, 1 through 10 is my raw data table. I'm going to format that as I should for my raw data table. And then I'm going to take my mean and my standard deviations. And actually, that, because this is not raw data, should not go in my raw data table. But it should go in my process data tables. So what I'm going to do is paste that down in here. And that is not the right data. Let's see. I want to format, paste the values, but notice that my decimal places are the same, so I'm going to fix that. I want 3 decimal places. Okay, so now the numbers match. And so what I'm going to do to do my ANOVA, I actually didn't need that. I will need that for my graphing. So I'm going to go and calculate my ANOVA. I'm just going to scroll down just a little bit. And what I'm going to do is you click on this data tab that you have up here. When I click on this data tab, I'm going to scoot my screen over to the right a little bit. I see this button over here which says data analysis. That's the button I want to click, but you may not have that installed on your computer. So to install that, you have to go to File, Options, Add-ins, and inactive application add-ins. You'll see this analysis tool pack, not here in active application add-ins, but in inactive. And when you click on it, let's say you click on this, let's say I wanted to add this add-in, you might automatically click on that and click OK, but that's not what you do. Nothing will happen. You click on this and you click Go, and then you run through it and it will get installed. But I don't need to do anything because I already have my analysis tool pack installed. So again, I'm going to come over, I'm going to click on data, make sure I'm clicked on data, and I go to data analysis, and I want the ANOVA single factor because I have one independent variable. I'm going to click OK, and I'm going to pick all of the data that I want it to analyze. So what I'll do is I don't want it to, well, I want the title or the numbers at the top, and all I want is the raw data. So I'm going to pick all of that data. I'm going to make sure that I've got this button checked that says labels in the first row. I've got an alpha set of 0.05, which is my 5% due to chance, which is automatically evaluating it at a 95% confidence level. My data is grouped in columns, and my output range, I actually want to pick a different cell. I actually want it to go somewhere down here. If you picked somewhere down here under all this data, things can kind of get messed up. You want to pick something, put it in a column or in a section that doesn't have anything already in that column. So I want it to go in this cell, and a whole bunch of data is about to pop out. So here we go. I'm going to scroll down just a little bit, and that, ladies and gentlemen, is all of my data. And I'll tell you, if you throw this into your IA, you are going to be in trouble, because that doesn't, you have to be able to tell me what all of it means. And you don't probably know, and it's okay that you don't, because it's not all important. So let me tell you exactly what's important here. You've got your averages here, which actually match our numbers here. They're just rewritten to different decimal places. And we have this ANOVA data down here, which is really, really important. So this value and this value and this value are the 3 really, really important values. Okay, and so when we look at this, let me see what I could do here. What happened to my pen? Okay. Oh, here we go. Okay. So what I want to do is I'm going to just highlight these values because that's really all I need as far as my ANOVA data. But there is some other important data or important things to consider here. So we're going to analyze this in exactly the same way we did with the t-test. So what I need is my F calculated to be larger than my F critical. And I need my p-value to be less than 0.05. Well, my F calculated is 14.54948, and that is greater than 2.246408. So that rule is satisfied, and this one should be too. They should correlate. So my p-value of 2.45 times 10 to the negative 10 is less than 0.05. If you don't know your exponents, this is negative 10, so I'm going to move this decimal 10 spaces to the back, and if we can imagine that's adding 9 zeros in front of this 2, and then putting in your decimal place, you'll notice that that number is much, much smaller. So that means that we can refute the null hypothesis, and the alternative hypothesis is supported. So we've disproven the null hypothesis. We've not proven anything, we've only disproven the null hypothesis. And I hope that makes sense, but let me scroll up here and show you how to make a graph of your data. Okay, so let's see how I can get out of this. Okay, so what I'm going to do is actually select just my means and my temperatures, and I'm going to go to, let me scroll up here a little bit, move this up. I'm going to go to Insert, and I want to scatter. Now you might be thinking bar, but the most appropriate way to do this is scatter, because that's the most accurate or appropriate way to represent this data. So here is my data, and it has plotted itself very, very nicely on my graph. And what I need to do though is add titles and axis labels and whatnot. So the way to do that is, once I've clicked on my graph, up here under chart tools, I'm going to go to layout, and here are my options for my chart title, my axis titles. If I need a legend, any data labels, this is how I label what I want for different choices for my axes. If I want to change my grid lines, there are trend lines and error bars, and so there's some different ways of going about collecting this data. But what I'm going to do is click first on any one of these data points, but really the first one, and then I'm going to right click on it. So bear with me just for a second, because I may make some mistakes here, but I'll walk you through it and we'll make sure it comes out right. So I'm going to right click on this and then click on Format Data Series. And what we're going to do is pick bear with me just for a moment. Okay, sorry. The directions I had were for an older version. So once you've selected your graph, you can select this data, you don't have to. And up here under layout, once I've selected layout, there's an option here with error bars. And you may be tempted to select error bars with standard error, or error bars with percentage, or even error bars with standard deviation. But I'll tell you that it displays only one standard deviation for each data set. So that becomes a little bit problematic. So each error bar will be the same, will have the same dimensions. And that's not true for each data set or each population of our data. So I'm going to click on more error bar options. And I want the direction to, the vertical error bars to be up and down, but in both directions, and I want a cap on them, and I don't want a fixed value. In fact, I want a custom value. And when I pick those specify value, I'm going to pick my data down in my standard deviation column, and I'm going to pick it again down here at the bottom, and that tells it to go up those values and down those values. I click OK, I hit close, and there we go. And so I have my plus or minus standard deviation error bars up and down on my graph. And one last thing to look at on this graph, you see that there are actually X or horizontal error bars on each of these, and so we're going to need to delete those. I'm going to delete this. I only have one data series here, and if you look at this, we might want to make this a little bit bigger. So I'm going to go ahead and move my chart to a new sheet. So I have a new tab that just popped open on the bottom, and this is that. So I can now click on my horizontal. Should be able to. Yeah. Okay, so my horizontal axes. And so when I go back to layout and error bars and more error bar options, I'm going to see that my value that it's set to is a fixed value of 1, and that's why you see them all at the same thing. But if I change that to 0, then what I'll see is that they go away, and I can hit close. And so now I've only got my X generated, Y along the Y-axis generated standard deviation bars. I want to make sure that that's indicated in my title that I've got plus or minus 1 SD. And when you look at this data, you can see that that there's a lot of overlap between different groups. But because my F value is so high, all that means is that there is some difference between some of the groups. And so if you look at my 10 degree group compared to my 20 and 30, they overlap. But my 10 and my 40 definitely don't overlap. My 10 and my 50 definitely don't overlap. And maybe my 10 and 70 don't. I don't know. But my 40 and 50 overlap, and my 40, 50, and 60 all overlap. But my 40 and my 70 don't overlap. And so that's a lot of analysis that you need to be able to talk about, is that maybe there's not enough of a difference in the enzyme action between 10 and 30 degrees, but there is a sizable and significant difference between 10 and 40. And the way to really verify that is to actually do a t-test between my data in my 10 degree Celsius category to find that mean and compare that mean to that of the 40 degree and verify that that t-value is larger than the t-critical based on my degrees of freedom. And that's a lot of analysis, and that takes time, and that's not a bad thing. It just takes time. So I'll leave it at that. I hope that raises some questions. It gives you lots to talk about and lots to think about. And basically, all you need to do is now take this graph and throw it into your Google Doc. But you want to make sure you've got all your axes labeled and that it's done before you do that. And the best way to do that is to print screen. So you have a button on your keyboard that's print screen. On my laptop, I have to hit function F11, and I get print screen. I'm going to throw that into Microsoft Paint, and then export that out as a JPEG. Maybe crop just the graph out, and then export that as a JPEG, and then upload it into my Google Doc. On my Mac, what I would hit is Command-Shift-4, take a screenshot, and just select my graph, and then upload that into my Google Doc. So there's shortcuts around that. If you need help with that, please let me know. Don't wait till the night before or the morning of to figure that out, because I may not be able to help you at that point. Okay? I think that's all.